which set is linear. Okay, all that's very, very popular. But now we need to talk about mechanisms. So how do we go from reactants to products? And the process that happens there, and kind of some species that might be involved but don't necessarily get altered. If we consider mechanisms is a very interesting field because it's really hard to prove mechanisms. So it's a little pie in the sky stuff. But we're going to look at the basics. Yes, pie in the sky. Like maybe it happens, maybe it doesn't. All right, so in terms of how many molecules are involved, all right, so unimolecular, bimolecular, termolecular, and most of them are uni or bi.
I was told Omar was not. The next time we're doing Omar something? Give me an interrupt like that.
No, Omar is not in until 5th.
Oh,
Who lets you out of your room anyway?
What? I'm gonna chill out looking for Omar.
It's not in here.
Okay.
I got him scared.
You're such a professional.
It's good. He doesn't try his normal garbage in here. He tries, but he tries to be sneaky about it. All right, so you need to write this down somewhere on that paper or on some notes or somewhere that you can find it easily. An intermediate is going to be a species that is produced in one step and then consumed in another. Okay, an intermediate does not show up in the balanced chemical equation. All right, so let me kind of lay out what we're going to look at and how we need to approach it. So up until now, we said that reactants go to products and that nothing happens in between. Okay, that's not true. So we might have steps involved in that process. And again, these are hard to kind of nail down because things like intermediates, they exist for sure, but they don't exist on a very long time frame. So we're talking like microseconds or maybe milliseconds if they're long lasting. And so they're hard to isolate. They're hard to prove that they're there. So some of this is maybe beyond pure speculation. All right, but intermediate is super important.
So that would, I'm not trying to like get ahead of you, but that would be like number one, the intermediate thing. Like the intermediate, is that what we're looking at?
Yeah.
Okay.
All right, so an intermediate is going to be produced and then consumed.
That would be the overall reaction.
So this would be step one, this would be step two in this particular section. I think now it's a little bit different on the next one.
I love drawing little arrows.
All right, so on this particular setup, hey, we're going to look at a couple of steps, and these are just something that we are taking the information that we have and trying to provide some type of explanation of how we actually go from reactants to products. Okay, let's say I tell you it's a two-step process. Right, so if I know that things are normally unimolecular or maybe bimolecular, okay, those are the two big ones. Like one molecule might decompose, or we have two molecules that collide in such a fashion that they change one another. So we could say that two of these NO2 molecules come together, and we know at some point we need NO as a product, and then we could have this intermediate NO3 that acts as a go-between. Right, so I could react that NO3 with CO, and we could produce our CO2, and then we could actually spit out one of our original NO2s.
Why would we only have NO2?
Right, so if we give one of these oxygens to CO,
Oh,
we still
okay,
have
okay.
NO2 left. Right? Here, it's kind of the same setup, like one of these guys is going to give an oxygen to the other, so one of them will have 3 and one of them will have 1.
And why does it have the little, is that equilibrium?
This is an equilibrium. This is the final step here, doesn't have equilibrium. Only if we have time to talk about equilibrium. All right, so let's go to the problem step. All right, so we're going to add this up like it's algebra stuff. Okay, so anything that is on the left and on the right goes away, like NO3. If I have, so that's a very similar setup, right, to what we just looked at. It's not coincidence, but we have two NOs on the left, right? So we can write that as 2 NO. Two.
Like 2 NO2?
Yes.
So then that gets rid of all the differences.
So I've got 2 on 2. I've got 2 NO, right? 2.
And that's the overall reaction.
So we add the 2 steps together. Okay, those are, we can think of mechanisms as steps.
So when it asks for the overall reaction, we're basically just adding them? Okay.
Will the equations always be, like, will we ever have to balance an equation before we do that?
Not that I've seen.
Okay.
Okay.
I never say never with AP.
Oh,
So
Yes, with-
just make sure it's balanced.
It should be with mechanism stuff, but. All right, so here's the neat trick on this one. And like, this is easy money points. There's some stuff that we looked at that's not easy money points at all. It's tough money points. Hey, this is easy money points right here. If we want to write the rate law, and this is the only time we can do this is through mechanisms, we're going to look at the slow step. So, okay, and the stoichiometry from the slow step tells us what the rate law is. All right, so we're going to write rate equals K, and then in the slow step we have a pair of NO2s. 2 NO2s, right? And so we take that coefficient, and that is going to be our exponent.
So that's alright.
This is your rate law right here.
So we just take the reactants and the slow step.
Reactants in the slow step, that's it. Probably want to write that down somewhere too.
And our exponent is however many we have. Okay, what if it's like NO2 and like CO? Would it ever be like that?
Yeah,
What would that be?
Would you put a plus?
NO2 and then CO.
Oh, would it be
So
like,
that's like your A essentially.
would it be like plus or
Oh,
can you write it?
Cause
Oh,
rate
okay.
looks like K bracket A with the M,
right,
right? And then it's B with the N.
right,
So there we only have an A.
yes. So if you had, let's say you had NO2 plus CO in your slow step, right? So the rate would be K times NO2 to the first power, CO to the first power.
Okay.
Right, so we can use the stoichiometry from the slow step. The reactants in the slow step, those are our exponents. Those are our orders. It's the only flipping time you can do that. You don't make a habit of it, because that's really easy. You get a method of initial rates, you're like, all right, cool. 2, right, 2, right, cool. There's a 2 right there. 2. Right.
Wait, so like the 1 and the 1, is that our M and N? What about this one? Do we just have an M?
Right, because you only have one reactant. Even though it's split up,
It's the same thing.
it's the same thing. So you could rewrite that as 2,
Right.
2. And so that 2 now becomes that 2.
Okay. And our M is the what?
The order,
So that would be the first order, that would be second. And like that one's first order?
this one,
Mm-hmm.
second, 1 plus 1.
Oh, yeah. You have to add the
M plus
exponent.
N.
So 2 plus N.
It's
is
all
3.
kind of coming together now,
Okay.
but
So
sorry.
it's starting to coalesce?
I had to remember the format for the rate thing,
Yeah,
cause I
I
was
need my
like,
4.6.
Yeah.
I was
Yeah,
like,
that's
I don't
it.
have
The
my
format,
format.
and I think on the method of initial rates, when I was grading that, I went through and changed the ones that didn't put it in that form. Because they're a stickler about that form on the rate law, because it's fairly easy to understand, relatively close. All right, so this, writing the rate law from the mechanism, and specifically the slow step in the mechanism, that's easy money. Right, our coefficients become our exponents. And all that's all right, so on number 2, right, so this is kind of a follow-up to that slide that we looked at previously.
We're writing the 2 different things.
Yeah, so now we're gonna kind of write the 2 steps. Okay, we have the overall reaction. Okay, we know that the rate law
so we'll be left with 1 each.
Alright, so going backwards from what we just talked about. Okay, this is gonna be one of your steps, specifically the slow step,
Right.
So that one.
okay?
Mm-hmm.
So I know that the reactants on my slow step are gonna look like that.
Okay.
know that these are going to be my coefficients. That's a one and
Right.
that's a one. Right, so really the only way to put those two together. That. And that's probably, that's the trickiest part of that one right there.
Wait, so that first one is our, like, first step?
This is the overall.
Oh, so now we have to make it a second one.
Yes.
Oh, okay. So it's gonna equal that at the end.
Right. So this is the overall. And that's the tricky part of that one, but like we know that there's one of these and we know that there's one of these and we know from this that we have to put it together. Alright, so now we're gonna use what we have left. Alright, so I'm gonna take this guy and I know for my overall I also have an NO left. Alright, I've only used one of them. So I'm going to take the NO2. And I know on this second one, on the second mechanistic equation, that this has to be my product. Because I haven't used this yet.
Alright.
And I need that, so I'm going to take this. Put it together with one of those. I'm gonna make two of those.
Wait.
It's like a terrible chemistry puzzle.
Oh! Yeah, because that cancels that out and then, okay, okay.
So on the top, it's NOCl, and on the second one, it's NOCl2.
For the overall, it's NOCl.
Right.
But the only way, like, right here, we know there's one, we know there's one, we know that we gotta put them together from this.
Oh,
And the
okay.
only way we can put them together is like this. Okay, this is the part that's,
Right, it's just like this, that lower number is,
yes. So we have to account for that. And so then we can use this as an intermediate, use that,
oh wait, I just forgot to write it.
combine it with our leftover NO, and we know that this is gonna be the product.
Cause on mine I had NOCl here, but then the other one it was NOCl2. And I was like, they have different subscripts, they can't cancel. Okay, so that was all, was just writing the equation. We didn't have to
And that one's
separate.
second order. On this one.
Second. Yeah, that's second.
Where did the UBers and ETSers go today?
The college?
It was like
Yeah,
a
it was
college
career
fair.
day or something.
Right before junior day?
When's junior day?
Tomorrow.
Oh.
Are we gonna miss this class for junior day too?
Oh
Leave
my
at 8,
gosh.
we leave at 8.
Oh really?
That's so
Hey,
not cool.
no freak
Looks like it's senior
No,
day
it
and it begins. Y'all ready to party?
Oh, heck yeah.
Is it really mandatory?
Yeah.
I think today was mandatory, and I think no.
It's terrible.
All right, so 3 is an intermediate catalyst setup. So we know an intermediate is something that is produced and then consumed. So a catalyst is just the opposite.
And then it's consumed and produced.
Right. So something that we have as a reactant initially and then a product later on. Like however you want to think of that.
So instead of like consuming it, you like cough it up.
Yeah. So you
Catalyst,
eat it, you're like, bleh.
Yeah, that's what this is.
Catalyst, you're like, bleh. Mm.
Like
I
a
was
dog.
just thinking like catalyst.
Dog
sweet,
is
consumed
okay. Dog
first.
is the catalyst.
It's not
Cat is
that.
the other one. That's what you need to know.
Yeah. So a catalyst is a reactant first and then a product.
So I
An intermediate is a product first and then If we're talking sequentially or in order.
Just as I was getting confident, I turned over the paper.
Smiley face. More smile. Oh,
Oh.
Wait, I'm fine.
Yeah, so I'm not gonna go through that. We put this in here because those jack wagons at AP like snuck this in.
I like equilibrium.
And it just, oh my gosh. So,
Equilibrium.
so bad.
That's what it looks like.
So we decided to go ahead and put that in there.
Why? I love the. So if it's slow, it's happy, and if it's fast, it's sad.
That's right. I can relate.
No, really? No.
Did we just do something today?
One of these I did
You're
away
finishing
with,
it.
and I can't remember which one it was. Like, honestly.
All 100 questions?
Yeah, we got to like 80. So we'll probably do that tomorrow too. Which I'm not complaining.
I won this shit.
Thank you. She rated
It
yours.
might have been that one.
Ooh,
I know she was grading some others.
All right, so let's talk about collision model and activation energy and those things that we have to overcome.
I love the sarcasm on your first bullet point.
Yeah, listen, me and my buddy's humor, it's like one and the same. If you hang around us at any point, like, just let the dry humor roasting begin.
Oh, I love dry humor though.
Because, like, it'll be like a coffee fest because we're roasting everybody.
I was just dad joke times 100.
Yes, only throw in some mildly dark humor and some science stuff.
Sounds fun.
I love dark
Someone should make a
science.
set one.
And like I said, he's the most brilliant person I've ever met. There's a gal that was there that worked for,
Gal.
her name was Ingrid Fritsch. Like, she was bloody brilliant too. And she was super laid back. I think she was a volleyball gal too.
Mr. Roll was totally destined to be
Like, she
British.
was,
There was a girl last night with the name of Five.
Oh my gosh, I can see with the British.
Not Piper.
You'd be
Five.
unstoppable.
Five.
Five.
probably related
Oh
to
my gosh.
Five from
My
Dan.
name's Ron.
Mr. Roland,
Yo.
can you talk in a British accent?
My British accent's terrible.
Ooh.
I think mine's okay.
Let's hear it, Kendall.
I need a sentence.
Just start
I need a
talking.
sentence.
Just start talking. Here, I'll read the. Okay, I get them mixed up. Sometimes it's more Australian than it is British, but. The suggested mechanism for the reaction between peroxide and ion is. See, that was more Australian.
Is.
Is.
Can you give me a Jamaican?
Huh?
I
Jamaican.
talk American and that's how it's
No.
Close to Southern sometimes.
I don't
How do we draw? How?
Yeah, it
what
does
is
creep
that?
in for me
That was so
occasionally.
fast. What is that?
Do you say lawyer or lawyer?
Lawyer.
Or attorney?
I just said
I say
lawyer.
lawyer.
I've heard people say lawyer, but
What do y'all say?
I said lawyer.
Lawyer.
You say winter, don't you? You say winter. I'm the
Winter.
only
With a T?
person.
Winter.
No, I'm the
What about
only.
winter?
I'm the only person I know who says winter.
Yeah, I try to put the T in there.
What about oil? How do you say oil?
Do you say oil?
I say
Oil?
oil.
Oil?
Oil.
What about caramel?
Caramel.
Caramel.
The only southern thing I say besides y'all is
Acre.
winter.
What?
That's how you. That's the only thing that gives me away.
What did
All right, let's see if we can put a picture to activation energy.
Okay.
If we look at our energy diagrams, if we go from reactants to products, okay, from where we start to where we finish, that is delta H. Okay,
Start to finish.
Delta H is a state function. It doesn't matter the path. Right? But there's also this energy that we have to overcome to get there that's not related to the delta H. Right? And so that's the activation energy.
Does that P mean products?
Yeah.
Okay.
And so that's a barrier that we have to kind of overcome. We can start to think about those sorts of pictures out there where the reactants start to break apart, or we start to have these pseudo bonds with the molecules that are going to bond together. And so we have this partial bond to this guy that I'm going to let go. I'm going to have a partial bond to this guy that I'm getting ready to bond with. So it's called a transition state, or a transition state. That's happening here.
Above the one?
Here in the activation energy part. Okay, so you have that transition state here. And then eventually we get down to our products. In the transition state, we can also have the pieces of the mechanism going on. So that's step one, or maybe step two, or maybe it's a step three. That happens in here. And there's a certain amount of energy associated with it. And that's been long been the discussion in terms of trying to find a way to solve it. And actually Arrhenius did it. How accurate it is, I'm not sure. All right, so if we have this collision model where if it's bimolecular, two molecules are going to collide, and we know that temperature is going to play a part in terms of average kinetic energy. But the second part is that they have to be oriented in a certain way. Orientation matters. Matters a lot. So there's a constant that goes with how it's oriented. And so there's your transition state here. We used to call it activated complex. I don't know if that's still the case. All right, so here's Arrhenius, and like honestly, there's not as much focus in AP on Arrhenius as there used to be. But I still like to kind of go through it because you may see it later on. Yeah, I think 2 or 3 years ago, I think I took it off the test. When AP decided it wasn't AP. And you've got obviously different factors here. A is a frequency factor that actually adjusts for both collision velocity and orientation. E sub A is your activation energy. K is your rate constant. Okay, that hasn't changed. It's still the rate constant. And then R and T are going to be your gas constant, but for energy, so the 8.314, and then temperature in Kelvin, because R is in Kelvin.
I feel like there's a kindergarten somewhere out there that has a kid named Kelvin.
Probably.
That's sad for that kid.
This is my kid Phosphorus.
Radon.
Thermo. Some millennial chem
Silicon.
geek is gonna name their kid. Silicon? That's the word. Xenon? My name's Xenon.
Bromine.
Boron. I like it.
Oh,
I'm gonna name my kid
that's
Boron.
horrible.
Moron? No boron.
That poor kid.
I feel like
Imagine
Xenon
what the
would do
kids will
that.
say on the playground. Boron, the moron. Come on now.
I love it.
I'd name the kid Chloe.
My name's Promethium.
That sounds great.
My lucky number is 61.
So this one fits in the bottom calcium, right?
Calcium.
So we can actually get rid of
Thallium for a girl.
the right hand side. I'm just gonna make
Your
sure I do it right.
uranium.
Not like this
Some make sense.
Could you?
What are you doing?
How do you say this?
Hey, Mr. Roland. How
That
do
would
you-
be child abuse.
Maybe. Do you? Okay, I'll ask you in a minute.
What name you?
Lauren.
It's not that important.
Okay,
so.
that's kind of
Ooh.
nice.
What?
Bottom.
Laurentium? I go by Lauren. Laurentium. Thorium.
I refuse to check my grade, guys. I think I got a
No.
0.
I kind of believe that you do better than
I kind of like rubidium. That I could go by Ruby.
I would think that you did.
That's perfect.
What?
I did it.
Name the
I can't remember
girl
which way it goes.
rubidium. And then have her go by Ruby.
Or just name her Ruby.
We'll have to try this one. Fine.
No! Rubidium!
All right.
Americium.
So if I've got, a lot of times we don't use Arrhenius in this form unless we have data. Like we have to have data to figure out what the heck A is. A is kind of the problem child.
Feel that.
You should.
Girl, you're just.
So we can compare temperatures, right? And I think, let's try it. I can't remember if this is 2 and 1 or if this is 1 and 2. Anyway, so if I consider 2 different temperatures, I can get rid of this constant because it's going to be the same for both. All right, so I can do the natural log of K2 divided by K1 is equal to the negative E sub A over R. All right, so our E sub A is going to be 102, but we have to put that into joules. So 102,000. And then R is going to be 8.314.
And that's gonna be up.
Yeah, I'm trying. I know that one is. This is the one that I'm.
Okay, so
I'm
our
100%
K2
sure.
is what we're looking for.
Yes,
T2 is the 65, but in Kelvin.
right.
And that's just 273 plus that.
Yeah. We're actually going through it.
Yeah. No, you can do it on your own.
All right, so
Oh, okay.
T2 would be your 65, change it to Kelvin. T1, 45, change it to Kelvin. Let's see what we'll come up with right there. See if that flies.
273, right?
Plus 273, yeah. Well, so to get to, okay, so you take 30 out of 65, then add it to that, now you're at 303, right? And you have 30
So you,
left over,
when you
so
do
I
that, you make your
33, but now you have 5
activation
left over,
negative.
338.
I mean, there's a negative sign out front. There's a difference there.
And I just split the 65 into 10s, and then you just add the 10s one by one, and then you add the 1s.
And you could do that so quickly in your head.
Well, because you divide the 10s into 2 30s, and then add by 3. Because what's,
45 is 1, right?
it's the gas constant, but I don't know if we have that, so I don't know. What are we finding? K2. What's K?
That,
No.
K2's what we're solving for.
Okay, then what's the second temperature though? They're the same. Are
The
they?
second temperature is 65 degrees Celsius.
Wait, but that's the first temperature. Are they the same?
Wait, what is the value of
What?
what's R supposed to be? Like, R?
8.314,
Okay.
Oh.
Oh.
because it's energy.
And
Yeah.
Mr. Roland, are the temperatures the same?
No.
Then what are the? We're only given one temperature.
No, 45 and 60.
45.
I got like the
Huh.
number,
Okay.
it looks reasonable, 4.9 and -30.
And check this out. So we know that 45 degrees is 20 less than 65 degrees.
No.
Oh wait.
So
Absolutely.
338
I like typed that
minus
whole
20 is
thing on the right side
318.
in at once.
That's what I
It's
did.
Yeah, cause I ain't trying
Why do
to,
we use 102
Figure out the
here?
bars.
Because that's estimation.
I mean,
102,000
I don't think
because
they
it's
should change
kilojoules.
what-
1,000.
So add 3 zeros today, okay?
right side, like, if you put on the right side. there.
That's a big
Oh my
old
gosh,
question.
I really get angry so
What?
But he didn't
much.
get
Really like,
the same answer.
it's actually I kind of like it.
Do you want to
I'll
perform
have
it?
to, I'll have to let you read it.
Oh, read it.
Yeah,
We're not
I'm
gonna sing.
No, because I have to see his guitar. I still have the guitar.
I can play the verbal guitar.
Ugh.
What are you talking about?
Okay.
Ouch. Okay.
So K
Oh, I
is
got
the
this.
5.00.
K, we don't know. Yes, that's K1.
Well, I got 5.01. So I typed all of, I used
And
my
then
exact
A to
answers.
the-
So
Yeah,
I,
me too.
I kept it as the
And then
decimal.
divide that
and then I
by
raised it to
5,
E.
e to the negative
And then I
4.
put it in there.
Ah, I had it right the first time.
Go, Mr. Roland! I had it right the first time too.
Wait, okay.
I'm so
Oh, well
good.
done.
No! I just did it all.
Wait,
Butt
dang it!
face.
You meant that!
Wait,
Yeah.
so K2
Darn
on
tootin',
top though?
Mr. Roland.
Yeah, like I was thinking in my head, if I flip them here, I need to flip them on the right side.
I have a question though, because since you're just subtracting them both, does it really, like, your answer should still be the same, right?
No, it.
Oh.
What do you mean the same?
Good thing I didn't reach that part yet.
So 318 is T1.
And divide that by 5.
Oh.
Yes, I got a very small number.
Oh, I got -2.
You gotta take the E of it.
I haven't done that yet.
That's what you need to do. Wait, did I divide? No, I meant multiply.
5.09.
Oh, butts.
Or 5.1
I like
times
this
10
one.
to the -5. That's what you got the first time.
I got 4.99 times 10 to the negative
Wait,
4
so I can multiply
whenever I
this
switched my
number
T1
out.
and T2.
5.1 e to the negative 5. Okay, Kendall, what did you get?
I got 4.99 times 10 to the negative 4.
That's not, that's okay, because it's time to go. So it's time to stop
I
thinking.
did it right the first time on my calculator.
So it is that?
What's the answer? Huh.
So just to clarify, the 65 degrees Celsius is our
It's
T2.
over by the fishbowl.
Yes.
Okay, bye.